Hi folks, welcome to a video on finding rational zeros. This goes with section 6.6 in your Algebra 2 book. After today, participants will be able to use the rational zero theorem to find possible rational zeros of a polynomial function. We're going to talk about what the rational zero theorem is. And then we're also going to find the rational zeros of a polynomial. Before we do these two things, the first thing we need to talk about is what is a rational number. Well, rational numbers are anything that can be written as a ratio of two integers, like 3/4, or +5, -2, things like that, zeros, all those kind of nice numbers that we've seen throughout the year, right? Irrational numbers are things, basically anything with a square root, square root of 2, or anything that has a complex number, like 3i. So these are numbers that we're not going to find, at least not initially, through the rational zero theorem. We're going to be sticking up here with numbers up here in the green that we're going to get. The second thing we need to know about is, what is a zero? Well, a zero, just very simply put, a zero is going to be an input into the function that makes the output 0. So for a very simple function like, let's say, f of x equals 2x minus, let's say, 6. Well, to find the 0, I would set f of x equal to 0 and then go ahead and solve this. So really, just you set your equation, or you set your function equal to 0, and you go ahead and solve this. And you can do the work here, but you're going to find out that x equals 3 is the 0 of the function. It's also a solution of this equation here. As it turns out, it's also going to be an x-intercept. So all these things are very interconnected, and we're going to see that in a later section coming up real soon here. So we're going to take a look at a solved problem here, and we're going to take a look at what's going on, and this is going to lead us to the rational zero theorem. Okay, so I'm starting off with this function f of x, which is 3x squared plus 2x minus 8. And the first thing I've done is I set the function equal to 0. And you notice here that it got factored, right? 3x minus 4 times x plus 2. I factored that right side. And then after you factor that, you would set each of those equal to 0. And we'd get solutions. We get zeros of 4/3 and -2. And I wrote it like this, as -2/1, for a very specific reason. We're going to look at exactly where all these pieces came from. And again, this is going to lead us to, or at least give us an understanding of the rational zero theorem. So let's take a look at where this 4 came from. This 4 came from, well, where? Well, it came from right there, right, that constant. And that 4 came from where? Well, it came from a factor of that 8. Okay, so again, this 4 down here came from up here, and that came from the 8. Okay, let's look at the other numerator. Let's look at this 2. Well, let's follow this backwards and see where it came from. Well, this came from the 2 right there, and that 2 came from, guess what? That 2 came from that factor of 8, right? That's how we factored that expression up top. So, as it turns out, both of these terms in the numerator, I'm going to get some of this stuff out of the way here. Both of these terms, the 4 and the 2, came from factors of this 8. Okay, that's going to be a key concept, and we'll see that in the rational zero theorem. So we'll come back to that in a second. Let's take a look at the denominator. Where did these things come from? Well, this 3, well, if we follow this back here, it came from that 3, and that 3x came from there. Okay, well, let's follow the other denominator. We have this 1 down here. Well, this 1 came from this 1x, and that 1x came from this 3x squared. So it looks like, hopefully you see a little bit of pattern here, right? Our denominators come from the factors of our leading coefficient, right? And we've seen that recently, right, when we looked at end behavior. And our numerators came from our factors of our constant. So if we have functions that we can't factor readily, sometimes we can use this idea, and we'll see the idea in a second here. We're going to use this rational zero theorem to help us out. Okay, let's take a look at what the rational zero theorem says. By the way, and this is new for us here, a little note here. After we finish this slide, you should be able to do homework problem number 1. And I'm going to continue this on throughout the rest of the slides today and in the future here. So if you ever lose track of what the numbers are for the homework, just watch the video and you're going to see all the homework problems at some point. Some of them might be at the very end. But you'll see them as we go along here. And you can pause the video at the end of the slide and then do that homework problem if you like. And you can just embed that right in your, into your notes. Okay, so here's the rational zero theorem. It says if your function f of x has integer coefficients, we need all just integer values, pardon me, this is sliding over, for coefficients, which is most of the time, right? Okay, then our rational zeros, right? Those nice zeros that are fractions and whole numbers and 0 and stuff like that, they're going to occur at, we call it this ratio of P over Q. We'll see how we're going to use that in a moment here. If you notice, this is a fraction that I have going on here, right? Big old fraction bar. Well, the numerator stuff, the stuff that is P, that came from factors of the constant. And I'm actually going to put plus or minus out here. We're going to see why momentarily. We're going to want to have that plus or minus there. So the numerator is going to come from factors of the constant, right? Just like back on this other slide here, the 4 and the 2, right? The 4 and the 2 came from factors of 8. Okay, and our denominator is going to come from factors of the leading coefficient. So I'm going to go back the slide real fast here, and remember where the 3 and the 1 came from, right? The 3 and the 1 both came from factors of 3, right? Factors of that leading coefficient. So that's the rational zero theorem, and it makes it kind of nice because when we can't necessarily factor, or even if we can factor, we can kind of do this what I call a last-ditch effort and get a list of what we call the possible rational zeros, and then we can go ahead and check them, and we'll see how we're going to do that momentarily. Okay, so at this point now, you should be able to accomplish homework problem number 1, which is, this is pretty much your answer right here, by the way. But anyways, you can go ahead and do number 1 if you like. Pause the video. I'm going to go on to the next example here. Okay, so for our next example, here we have our function g. And the first thing we're going to do in part A is we're just going to state the possible rational zeros for my function here. And then in the second part, we're going to find the actual rational zeros. So when I look at this function g, first thing, if you notice, it has 4 terms. So we might want to try to actually factor this as it turns out. And you can actually try to factor this if you like. 4 terms, how would you try to factor that? Well, I would try grouping. As it turns out, it's not going to group. Okay, so this is, but we're still going to be able to get some zeros out of this. So I'm going to just list all the possible rational zeros. I'm down over here. I'm going to list the possible rational zeros. So here's what I'm going to do. I'm going to make a big old fraction bar. Actually, I'm going to write this out first. Yeah, I'm going to use a fraction bar. I'm going to put, and you don't need to do this every time. I'm just doing this for the first time so we see where these numbers are coming from. I'm going to put a plus or minus. And I'm going to write the words factors of, I'm going to write 10, right? Because 10 is my constant. Actually, it's negative 10, isn't it? Okay. So factors of 10 over my factors of my leading coefficient, which is 1. So I'm going to list it like this. So what I want to do is make a list of all the factors of 10. And I guess I can just think of it as positive 10. That's fine. That's going to work. Okay. So what are all the factors of 10? Well, start low. Start with 1. 1's always going to be on the list, right? Because 1 goes into everything. Okay. So 1 times what gives me 10? Well, that's going to be 10. And I'm going to put 10 way down here on the other side. I'm going to put plus or minus 10. Put a little comma there. Okay. So 1 times 10 gives me 10. Okay, well, just now work up the list of numbers here. I tried 1. Does 2 go into 10? Well, yeah, it does. Okay. So I'm also going to put plus or minus 2 as a factor of 10. Well, 2 times what gives me 10? That's going to be 5. And as it turned out, I actually kind of spaced this out nicely. a lot of times what's going to happen is you get this big old space in the middle because you kind of space this out really far. But anyways, there's all my factors of my constant, all my factors of 10. And now I want all my factors on my leading coefficient. Well, all the factors of 1 are just 1. Okay, so here's what I'm going to do. Here's going to be my list. I'm going to now finish up part A. What I'm going to do is I'm going to take my numbers in my numerator one at a time, and I'm going to put them all over each combination of the numbers in my denominator. Well, there's only one combination in the denominator, right? There's only one number down there. So my first list of numbers are going to be plus or minus 1 over 1, if you will. Another number is going to be, another two numbers actually, is going to be plus or minus 2. We're also going to have plus or minus 5, again, over 1, and plus or minus 10. Those are all my possible rational zeros. There's going to be no other rational number besides these 8 that are here, right? Plus or minus 1. There's actually 2 numbers there, right? There's plus or minus 2, and so on. There's no others besides those 8 that possibly could be a zero of our function here. Okay, so now that I've generated this list, that's part A done. Okay, now I want to find the actual rational zeros. Of these 8, which of these are actually zeros? Okay, so what I'm going to do, I'm going to do this one at a time. I'm going to always start with positive 1. That's often on our list of our actual rational zeros. So I'm going to start with that. And essentially what I'm going to do is I'm going to plug it into G and see if my output is 0. Now, I'm going to use synthetic substitution. We've been using that a lot lately, and hopefully you're pretty comfortable with it now. You can't just substitute it directly. I'm going to strongly suggest that you do synthetic substitution. You're going to see why here in a moment. So I'm going to grab my coefficients for my function up there, right? I'm going to have 1, negative 2. I guess I should make my bars here first. Negative 2, negative 13, negative 10. And I'm testing positive 1, so I'm going to put positive 1 out here. And now I can actually move this up and get some room. And I'm going to go through and I'm going to do my substitution. What I'm looking for is, do I get a 0 out here? Right? Is my remainder 0? Is my output 0 here? It's really a question. Let's see how this works out. So let's see how this works. Remember, we add down. I'm not going to reteach synthetic substitution. I'll let you guys play around with that if you need to, or go watch the previous video. So anyways, I'm going to get a 1 here, add down, negative 1, multiply, negative 1, add down. Let's see, add down, negative 14, multiply, negative 14, and do I get 0 there? No, not even close. Okay, so it looks like 1 is not going to be a 0 of our function. So essentially all this stuff that I just did here was really kind of for naught. So basically, I guess I could leave it there if I want to. I really need to do this again. Oh, I'm not going to try 1 now. I'm going to put all my coefficients up here again. 1, negative 2, negative 13, negative 10. And I'm going to go up to my list. And I've tried positive 1. That doesn't work. I'm going to try negative 1 now and see if that works. So I'm going to put my negative 1 out here, and I'm going to go ahead and do my synthetic substitution. And, oh, look what happens this time. I add down this last term, and my output is indeed 0. This is 0. So negative 1 is a 0. Nice how that works, isn't it? Okay, so that's, negative 1 is a 0 of my function. Okay, here's the neat part. We started out with a cubic, right? This was x cubed minus 2x squared minus x minus 13x minus 10. This down here is now a quadratic, right? We've seen this before, right? Where our constant's negative 10, we have a minus 3x, and this is plus 1x squared. So I'm actually going to rewrite this as you see it. And now, this is now a quadratic. If it's factorable, we should go ahead and factor it and then solve it that way. That might be easier for us. Another option is we can go back to our list. I'm going to go way up here. and we have these other numbers to check, plus or minus 2, plus or minus 5, plus or minus 10. We certainly can do that, and we can continue with our synthetic division. I'm actually going to factor this because we can. And this is going to factor to x minus 5, x plus 2. And I'm going to set that equal to 0. And then I'm going to break these up. Right, x minus 5 equals 0. Oops. Or x equals 5. And x plus 2 equals 0. Or x equals negative 2. So my zeros then, just to bring this all together, we said negative 1 was the first one we found. Negative 2 and positive 5. Those are all the actual rational zeros. And again, they come from our list of possible rational zeros. One more thing before we get off this page here. I happen to go in the order of, I'm going to go back up here to my list, clean this up a little bit. Remember, here's our list that we did in part A of all of our possible rational zeros. I happen to choose, well actually I started by choosing positive 1, didn't I? Right? I tried positive 1, it didn't work, right? This number down here was not 0, okay? So I threw that one out and I tried a different number. Well, if I started with something that wasn't 1, if I started with, let's say, negative 2, what would have happened? Well, we would have found out that that was a 0, right? Because that's part of our answer, way down below, okay? So negative 2 was a 0. If we had gotten lucky and started with that, we would have found that out. It would have been a different factoring down here, right? This line right here would have been different, but we still could have done that. So there's different roads of getting there. Again, I would start with the low number, start with something easy like 1, negative 1, go to 2 if that's there, negative 2. But you should eventually get down to something that is a quadratic, like this is. That you can factor or solve by other methods. Or again, if you want to keep with synthetic division, you may go ahead and do that. Okay, hopefully that this one was useful because that's really kind of the main idea here. At this point, you should be able to tackle homework problem numbers 4 and 7. We're going to do one more example here. It's a little bit amped up, not too much more. We just have denominators that are just more than just 1 there. So we'll see what happens there. But this really is kind of the gist of what the rational zero theorem is and how we use it to find the actual zeros. So we'll do one more here and then we'll call it a day. Okay, so we're going to find the real zeros of f, which is 2x cubed plus 9x squared plus 19x plus 15. And so again, what I'm going to do, this is just like before. The only reason why this is a little bit amped up is because we have this factor of 2 as a leading coefficient, and 15 has a few more factors than what we had with 10 in the previous problem. So the first thing I'm going to do is I'm going to list my possible rational zeros. So I'm going to make my big old fraction bar, and I'm going to list all my factors of 15. So I'm going to start with 1, I'm going to go way out here, and 15. Okay, does 2 go into 15? No, 2 doesn't go into 15. Okay. Does 3 go into 15? Yeah, 3 goes into 15, and it goes in 5 times. Does 4 go into 15? No, it doesn't. And I've gotten up to, once I get to 4, 5's on the other side, so there's nothing else that's going to go into 15. I have all my list. Here's that space that I was talking about before. I kind of put that 15 way out to the side. But that's fine. That's just my list. Okay, so I now want to find factors of my leading coefficient. Well, that's going to be 1 and 2. And I don't need to put the plus or minus there because I really have it up top. So here's my list, and it's going to be several numbers here. So I'm going to take my first term up top and my first term in the denominator, and my list is going to start with plus or minus 1, because that's what 1 over 1 equals, right? Okay. And then I'm going to take my first number up there and the next number on my list in my denominator. And the next set of numbers is going to be plus or minus a half. Those are also going to be possible rational roots. And I'm going to do this for every term up top and every term down below. I'm going to do plus or minus 3 over 1, plus or minus 3 over 2. So, comma, plus or minus 3 over 1, plus or minus 3 over 2. I'm going to do the same thing with 5 over 1, 5 over 2, plus or minus 5, Actually, I'm going to start this on a, I'm going to move this a little bit because I have a little picture that's going to come in here momentarily. So I'm going to make a little room for myself, or my little commas. All right, so what did we say? Plus or minus 5 over 1, plus or minus 5 over 2. We have 15 over 1, and 15 over 2. And if you look at this list, this is not really a short list. So we can just go and start plugging some stuff in if you really want to, but that's really going to kind of be, it's going to take a long time if we don't get it right away. So what if I give you the additional information that this is a graph of our function? Can you see where there's an x-intercept, or at least approximately? Well, there's an x-intercept right around there that's somewhere between -1 and -2, right? So do we have anything on the list that's somewhere between -1 and -2? Well, this is exactly -1, +1. No, actually both of those are out. -0.5, no, that's not there. Is it -3? No. -3.5 maybe? Yeah, that looks like that's between -1 and -2. Is there anything else? Plus or minus 5, probably I can cross these off, right? No, that's not on our list because there's no zeros there. -2.5, that's close, but nope, that doesn't work there. Plus or minus 15, nope. Plus or minus 15.5, that doesn't work. The only one that's even close, and again, I'm looking at the 0 over here, that looks like it's somewhere around -1.5, and luckily that's on my list. So that's what I'm going to use to do some synthetic substitution. So unfortunately, it's a fraction, so I'm going to have to deal with some fractions here. But that's life. That's how it goes. So I'm going to try -3/2, and I'm going to do synthetic substitution with my coefficients up here. So I'm going to grab 2, 9, 19, and 15. Oops. There are my answers down there. Actually, those aren't my answers. Those were for a different problem here. So luckily, you can just follow along with me. We're not going to come across fractions too often. So this might be the only time that we actually do this. So again, I'm going to add down 2, 3/2, excuse me, -3/2 times 2 is going to be -3. Add down is 6. Multiply again. Whoops, maybe that's not all there. Okay. Anyways, -3/2 times 6, I'm going to get -9. Add down is 10. Multiply is -15. Yay, look at that. Okay, I get a 0 here, right? I get 0. That means x equals -3/2. That's a 0 of our function. Here's the cool thing about this. If you go back up to the picture here, and if you had a wider picture, we could actually see this, but just take my word for it here. For at least the ones you see, this will be hopefully make some sense here. All these numbers that I've crossed off, get some of these out of the way at least, plus or minus 1, plus or minus 1/2, and all the way down the list, none of these are zeros, right? +1, -1, there's no x-intercepts there. Plus or minus 1/2, plus or minus 3, right? All those points, there's no x-intercepts there. So those aren't possible. Those are not possibly rational zeros because I can see the picture. So the only one that I can actually see there is -3/2. So that's the only rational zero from anything on my list. And again, take my word for it with plus or minus 15. Yeah, that's really the only one that we need to worry about. Plus or minus 15, it doesn't come back down and go through those points there. So we're done here. We found the zero, the x-intercept, for our function, luckily. So okay, let's wrap this. Oops, let's not do that one today. So did we do what we said we were going to do? Did we use the rational zero theorem to find a list of the possible rational zeros? Well, yeah, that was the whole idea with with making our list here, right? All of this wonderful stuff which has all my markings on, right? That's just a big long list of all our possible rational zeros. And then we find the actual rational zeros of a polynomial. Yeah, we did that, and that was through our synthetic division, right? Okay. So I hope that you found this useful. Sorry this went on a little bit longer than I planned, but hopefully you found this useful, and you can take a shot at those homework problems, and I'll see you guys next time in class.